Yet something else rises to take control beyond those scales. A little over 6 billion years ago, the universe passed a quiet milestone. Before then, gravity from matter, both normal and dark, was slowing the expansion. After then, an energy density with negative pressure, something we call dark energy, began to dominate. It doesn't clump into halos the way matter does. It doesn't dilute as fast when space expands. In the simplest model, it does not dilute at all. It is constant energy per volume, making new space energetically like old space. If that is right, then, as the universe grows, the share of total energy in matter keeps thinning out, while dark energy's share rises to nearly all. The result is an acceleration of the scale factor, an accelerating expansion. That change is not a force wind pushing galaxies apart. It is a global change in the way distances evolve with time when gravity no longer has the upper hand on huge scales. You can see the signature of this acceleration by comparing how supernovae of the same type look at different redshifts. Many are dimmer than they would be if the universe had simply coasted after the Big Bang. You can sense it in the way galaxy clustering grows over time, slowed by the same accelerated expansion, and you can measure it through the scale of those baryon acoustic features in maps of the universe. Dark energy's equation of state, the relationship between its pressure and energy density, seems close to nu equals -1, which corresponds to a cosmological constant, a simple curvature of time and space that Einstein first wrote down and then abandoned in a moment of regret. If it is exactly -1 and unchanging, then the universe heads toward a de Sitter future, a space-time with an event horizon, not because of a wall in space, but because of the way light paths curve. Event horizon is a loaded term we usually reserve for black holes, but the universe in an accelerating phase has a similar horizon. Not everything we can see today is something we can ever talk to. A galaxy that is simply too far away, receding too fast because of the expansion, can keep sending light that reaches us only if that light left when the galaxy was nearer. If it emits light now, that light might never cross the expanding gulf to arrive. There are 3 surfaces worth distinguishing. The particle horizon is the boundary of everything, whose light has had time to get to us since the Big Bang. Today, it sits at a proper distance of about 46 billion light-years. The Hubble sphere is closer, around 14 billion light-years. The distance at which the recession speed equals the speed of light right now. But the Hubble sphere is not a true horizon. Light can leave a galaxy outside that sphere and still reach us later as the Hubble radius changes. The event horizon is the hard limit on signals sent now that will ever be received. Measured today, its radius is about 16 billion light-years in proper distance. Inside that, a message we send today, a photon, a radio signal, a spacecraft, if we could accelerate it arbitrarily close to light speed, will eventually reach. Beyond that, even light we emit now is chasing a receding target so fast that it will never catch up. It is the imprint of new space woven in between wave crests during the flight. You can watch it in supernovae. The brightening and fading of explosions in distant galaxies take longer by the same 1 plus z factor. On top of redshift, we add standard candles and standard rulers, Cepheid variables whose periods reveal their intrinsic brightness, the tip of the red giant branch, type 1. As supernovae as nearly standard luminous peaks, surface brightness fluctuations, Tully-Fisher relations linking galaxy rotation and luminosity, and on the largest scales, the baryon acoustic oscillation scale. a frozen-in sound wave from the early universe that leaves a preferred separation of galaxies at roughly 150 megaparsecs in car-moving coordinates. Stitch those rungs into a distance ladder, and then weigh the expansion with multiple independent checkmarks until a consistent picture forms. Within the genuine uncertainties, the core story keeps appearing. Space expands. Far things recede. The deeper you look, the earlier the scene. So, what is the nearest far? We said earlier that Virgo is about 54 million light-years away and receding. That is just down the road in cosmological terms. Beyond Virgo and surrounding it is a basin of gravitational flows called Laniakea, the supercluster scale region where galaxies tend to stream toward a focal area that historically earned the name the Great Attractor. Names can mislead. Supercluster suggests a bound monster. Laniakea, some 500 million light-years across in the sense of its attraction basin, is not a single object. It is a network of filaments feeding clusters, embedded in the universal expansion. Our local group swims in one of its streams at some 600 kilometers per second, relative to the rest frame of the cosmic microwave background, as measured by the CMB dipole. That speed is our peculiar velocity, motion atop the expansion, caused by the gravity of nearby structure. Peculiar velocities matter for mapping the nearby universe. On small scales, they dominate. On larger ones, the Hubble-Lemaitre expansion drowns them out. Past a few hundred million light-years, the recession is clean, and the peculiar bumps average away. The average number of baryons, ordinary matter, outside of galaxies is so low that in the typical intergalactic medium, you might count a few atoms per cubic meter, and in the deepest voids even fewer. And yet, half or more of the universe's ordinary matter is thought to be out here, warm and thin in the filaments, detected indirectly through faint X-ray glow or the signature of oxygen-absorbing quasar light. On the outskirts of clusters, gas densities rise to a few particles per cubic centimeter and temperatures jump to tens of millions of degrees. In that pressurized bath, galaxies share space but don't collide too often. The average separation in a rich cluster can still be hundreds of thousands of light-years. Imagery compresses that into a bright mosaic. Reality stretches it out into more dark than bright, more between than there. But distance in cosmology isn't just a ruler you place in space. The sky we see is also a history book. When you look at a galaxy a billion light-years away, you are seeing it as it was a billion years ago. That is the look-back time, the time light spent crossing the changing universe to reach you. Meanwhile, the proper distance to that galaxy now is larger than a billion light-years, because space has expanded during the journey. There's another helpful number, the co-moving distance. Imagine painting grid lines on the universe that expand along with everything unbound. The co-moving distance between those grid lines is fixed by definition. When astronomers talk about the co-moving separation between the Milky Way and a distant galaxy, they mean the distance you'd get if you stretched the universe back out to today's scale while keeping track of where things sit on those expanding grid lines. Look-back time, proper distance now, and co-moving distance are three ways to say how far we are from something that is receding and aging and sometimes changing shape while its light is still in flight. Because those lights are shifted. Every photon from a receding galaxy is stretched to longer wavelengths by the expansion. We call that redshift, and we label it with a simple number z. The scale factor of the universe at emission is 1/1 plus z. So a galaxy we see at z equals 1 was shining when the universe was half its present size. Its light has been stretched to twice the wavelength it had when emitted. That doubling is not a Doppler shift from motion through space, but even a glance outward from the local group begins to rewrite the word. Past the faint halo of nearby dwarfs like the Large and Small Magellanic Clouds, past the Triangulum Galaxy about 3 million light-years off, you step into a sheet of galaxies tens of millions of light-years across. The Virgo cluster, a rich swarm of thousands of galaxies, waits roughly 16.5 megaparsecs away, which is about 54 million light-years in today's units. Most of those galaxies are receding, not because something is pushing them through space, but because the fabric of space itself is stretching between structures that aren't bound together. The Hubble-Lemaitre law gives a first blush guide. Every megaparsec of separation adds about 70 kilometers per second of recessional velocity, depending on which measurement of today's Hubble constant you prefer. That number is not perfectly nailed down. Some methods find around 67, others around 73, and that disagreement holds open an active question in cosmology. But the pattern is solid. A galaxy 100 megaparsecs distant is carried away by the expansion at something like 7,000 kilometers per second today. The greater the proper distance between unbound structures, the faster they recede. It's tempting to stop there and say, fine, the universe inflates distances like a balloon, and that's all there is. But it isn't a balloon. Gravity sculpts the web of matter into groups, clusters, filaments, and voids. The expansion doesn't bulldoze those structures away. It only separates the islands that never had enough gravity to pull together. That is why the local group holds fast, Virgo holds fast, and the Coma cluster around 100 megaparsecs away holds fast. What's in between doesn't. The in-between is dominated by the faintest form of scenery. Gas warmed to millions of degrees in clusters, tenuous plasma threading filaments, and whole volumes with nearly nothing in them at all. The Boötes void is a famous example, roughly 330 million light-years across, with only a smattering of galaxies. It isn't a perfect sphere, and it isn't completely empty, but it is the shape of how gravity failed. The cosmic web, the great network revealed by surveys like Sloan and 2DF, gives you a visceral sense of scale. Walls hundreds of millions of light-years long, filaments tens of millions wide, and between them cavities where a beam of light could cross almost unchallenged for ages. So, when we say the distance between galaxies is worse than you think, we also mean that most of the volume between them is not just dark. It is starved of mass. Across the darkness between galaxies, the numbers sound simple, and then break apart in your hands. The average distance from a galaxy like ours to its nearest big neighbor is a couple of million light-years. Yet that gap is not empty, and it's not still. It's part of a fabric that is stretching, a web bent by gravity, punctured by vast voids hundreds of millions of light-years wide, and driven by an ingredient we don't fully understand: dark energy. The distance between galaxies is worse than you think because it changes what can ever touch, what can ever be known, and what can eventually disappear from the sky. If you want to follow that journey with Cosmo Depth, like this video and subscribe now, because the first answer is only the beginning. The real question is what can ever send a message back. We should begin close to home and test the word distance on familiar ground. You live inside the Milky Way, a spiral disk roughly 100,000 light-years across, cradling a few hundred billion stars and a far larger ocean of dark matter that we never see directly. From our position, 2/3 of the way out from the center, the nearest large galaxy is Andromeda. If you've ever seen it from a dark site, it's a chalky smudge. In truth, it's a sprawling pinwheel only 2.5 million light-years away in proper distance today. Proper distance is the distance you'd measure if you could freeze the expansion of the universe right now and stretch a ruler through the void. At this scale, gravity dominates. Andromeda is not drifting away with the general expansion. It's coming toward us at about 110 kilometers per second. The local group, about 50-odd galaxies, most of them faint dwarfs within a few million light-years, is a gravitationally bound family. Here, the expansion of space is not pulling us apart because gravity already won. The Milky Way and Andromeda will merge in about 4 to 5 billion years, leaving behind a larger, probably elliptical galaxy. On these scales, distance behaves like we expect. You can add velocities, watch orbits, predict collisions, and hear the phrase, "worse than you think," acquires a new edge. If you imagine that distance simply costs time and effort, the event horizon erases that dream. Suppose you point to a galaxy 5 billion light-years away in proper distance today. Its redshift might be around 0.8, its look-back time around 7 billion years. You ask, could a civilization with a starship cruising at 99% of light speed ever visit? They could cross 5 billion light-years in their own onboard time in a few decades because of time dilation, right? Relativity allows that strange truth in a non-expanding space-time. But in the real universe, what matters for reach is not just your proper velocity, but what the expansion does in the meantime. There are subtleties in defining speed over cosmological scales, but the sobering summary is this: no one can outrun the event horizon with a signal that obeys the speed limit of light. A one-way trip might reach a galaxy whose light we see today far beyond 16 billion light-years, if the traveler rides the swelling space and never looks back. But any hope of returning a report to us, or even sending a pulse beamed backward, is bound by the event horizon from the start. We can take these ideas and start putting numbers in your mind that change the way the sky looks. Raise your eyes to a galaxy at redshift z equals 1. Its light has taken around 7.8 billion years to get here. When it emitted the light we now see, it was perhaps 5 billion light-years away, in proper distance then, in a universe half its current size. Today, if you could freeze the expansion and draw a line, that same galaxy is roughly 10 billion light-years from us. Its recession speed, by Hubble's law, is around 700 kilometers per second per megaparsec, times about 3,000 megaparsecs, so on the order of 200,000 kilometers per second. That is 2/3 of light speed in the language of recession, which is not in conflict with relativity because it is space expanding rather than an object moving through space. That galaxy is still within the event horizon. Send a photon today, it will reach. Aim farther, to z equals 2. The look-back time is around 10.3 billion years. The proper distance now is about 16.3 billion light-years. That's on the edge. For z equals 3, light from when the universe was only a quarter of its current size, the proper distance today is around 20 billion light-years. Signals we send now cannot get there, not ever. Yet we can see those galaxies because their light left while they were closer, and while the universe's expansion was slower. The idea of reach separates from the idea of visibility as the universe ages. The observable universe, everything we can see now, is a sphere of about 46 billion light-years in radius measured in proper distance today. It contains on the order of a few hundred billion large galaxies and far more dwarfs, though counting is tricky. For years, Estimates based on deep images suggested perhaps 2 trillion galaxies if you include tiny ones beyond current detection. More recent work with better data argues for fewer, maybe in the hundreds of billions, as our census of faint galaxies improves and models of early star formation adjust. No one knows the exact number, and it is not a single number forever because galaxies merge, shut down, and fade. But only a fraction of those are ever within our event horizon for signals sent now. If you take a rough number for the number density of galaxies, say around 100th per cubic megaparsec as a ballpark, then the event horizon's volume contains on the order of billions of galaxies today. That sounds generous until you remember what forever does to a number like billions. Over time, more and more of those galaxies will slide over the event horizon for anything we emit at later times, even as light they emitted long ago still drifts toward us. Future observers will inherit a night sky that remembers everything near and forgets everything far, sentence by sentence. Before we leap into that future, it's worth settling one common confusion to keep our language honest. People sometimes say the expansion of the universe is pulling galaxies apart as if it were a friction or a wind. It isn't. On small scales, general relativity allows spacetimes that are effectively islands. The metric inside a bound system is well described by Newtonian gravity or even by special relativity. Galaxies do not expand because the gravitational or electromagnetic forces inside them are stronger than some opposing pressure. Rather, the equations that describe a stable galaxy are not those of a uniform expanding spacetime in the first place. The local solution and the global solution patch together rather than fight. And there is no edge where the expansion stops and gravity begins. Instead, think in terms of a turnaround radius, a place where the pull inward from a concentration of mass balances the general expansion outward so that matter stops participating in the Hubble flow and begins to rain down. For the local group, that radius is on the order of a megaparsec. At that scale, dwarfs wobble into orbit instead of drifting away. How do we know where we are in that grand balance? Because the sky is full of rulers and clocks if you learn to read them. The nearest rungs of the distance ladder are almost shockingly direct. Gaia measures the parallax of stars by tracing the tiny wobble caused by Earth's orbit. Millisecond shifts corresponding to distances of thousands of light years. That fixes the brightness of standard candles, like Cephids, whose pulsation periods tell us their true luminosity. From there, we extend to the tips of a red giant branches in distant galaxies, to Type 1, a supernovae that can be seen out to gigaparsec distances, to surface brightness fluctuations in elliptical galaxies that reveal granularity and thus distance, and to Tully-Fisher and Faber-Jackson relations connecting galaxy rotation or velocity dispersion to absolute magnitude. Parallel to candles, we lay down standard rulers. The cosmic microwave background, a nearly perfect blackbody glow at 2.7 Kelvin, maps tiny temperature variations that encode the universe's content and geometry. The baryon acoustic oscillations appear as a faint bump in the galaxy correlation function at about 150 megaparsecs co-moving, a kind of fossilized ripple whose size we can calculate and then observe. These cross-checks yield distances as a function of redshift and pin-down parameters like the Hubble constant h0, the matter density omega m, and the dark energy density omega lambda. The fact that different methods find slightly different h0 values is not a failure of the idea of expansion. It's a sign that our measurements are good enough to clash, and that there is room for new physics or hidden systematics. Either way, the data say the same thing. When we look far, we look back. The scale was smaller. Gravity assembled structure from noise, and for the last several billion years, dark energy has been taking over the timetable. Those timetables become humanly vivid when we count what will and won't remain neighbours. The local group today spans roughly 3 million light-years and contains a few dozen known dwarf galaxies. The Magellanic Clouds, about 160,000 and 200,000 light-years away, are satellites of the Milky Way. Andromeda holds its own faint retinue. In 4 to 5 billion years, our spiral will blend with Andromeda's into a larger system, sometimes nicknamed Milkdromeda. The Triangulum Galaxy, a smaller spiral close to both, may be captured by the new giant or orbit it. As star formation winds down and gas is consumed or heated, the merged galaxy may glow redder and quieter. All the while, everything beyond the local group continues to recede. We are falling slightly toward the Virgo cluster now. Peculiar velocity works like that, but the turn we would need to bind to Virgo is too tight. As dark energy continues to dilute the relative importance of gravity on large scales, the local group won't join Virgo. Instead, it will become an island on a black ocean, lit from within by the last echoes of its original starlight. Pull further back in time and the scales widen. At redshift Z approximately 6, the universe was less than 1 billion years old and was undergoing reionization, a phase transition where the first stars and galaxies flooded the universe with ultraviolet light, stripping electrons from hydrogen atoms and making space transparent to shorter wavelengths. Look-back time is about 12.8 billion years. The proper distance to those galaxies now is in the ballpark of 27 billion light-years. The growth from then to now took place on a web seeded by tiny quantum fluctuations stretched by inflation in the universe's infancy. Those fluctuations left anisotropies in the microwave background at the level of tens of microkelvins. From such small beginnings came the skeleton of filaments that define where galaxies form. The distances down the branches of that skeleton, the spacing between clusters, the width of filaments, the diameter of voids, carry the imprint of that beginning and the slow contest since between gravity's patience and dark energy's persistence. Everything we have learned about distances also reinterprets the phrase visible universe. There is what we can see with instruments at our time, and there is what we could ever see in principle, given the speed of light and the way the scale factor evolves. Today's particle horizon at about 46 billion light-years includes the oldest light we can collect. The CMB photons released about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into hydrogen and allow light to travel freely. That sphere swells as time passes because more light has time to travel, but because of accelerated expansion, the difference between what is eventually visible and what is now visible is not infinite. The observable universe's size will grow by a finite amount. We will add some brand new, first-time arrivals to our catalogue in the deep future. Photons just now starting their journeys to us from galaxies near our event horizon. But the volume of new territory is smaller than you might guess. Meanwhile, another slicing of the universe shrinks. The region that is causally connected in the future for signals we emit now. That event horizon asymptotes toward a fixed proper size in a cosmological constant universe. It settles around 16 billion light-years. That means the set of galaxies we could ever influence is a bubble that is not growing past a point. For living beings, this introduces a paradox that feels personal. Astronomy, is a study of unreachable places. Even nearby galaxies are beyond the scale of any mission our species could build in 1,000 generations. That fact would be sobering if space were static. In an accelerating cosmos, it also becomes a story about windows closing. One of the great intellectual tasks of the next 100 billion years, if creatures are still around to take it on, will be maintaining a record of things that are no longer there to be discovered again. As galaxies beyond our local group are carried outward, their light is stretched to longer and longer wavelengths. In roughly 100 billion years, the cosmic microwave background's peak wavelength will be redshifted to lengths so great that interstellar plasmas could block it, hiding the afterglow of the Big Bang itself from direct detection by any telescope living inside interstellar gas. The galaxies that provided proof of expansion by their recession today will have dimmed beyond detection, all but the local island. Cosmology will look different to those late astronomers. The only light left to diagnose the past will be local fossils. The heavy elements in old stars, the kinematics of globular clusters telling tales of long-gone mergers, and maybe fossils embedded in gravitational waves. Researchers have already explored this paradox on paper. In a de Sitter future, evidence for the Big Bang recedes behind practical horizons of instrument and context, yet the distances we face are not only a set of diminishing returns. They are also a guide to where we still can learn. Between us and the horizons are layers of the universe filled with information. The Lyman alpha forest of hydrogen absorption in the ultraviolet spectra of quasars mapping intergalactic gas. The Sunyaev-Zeldovich effect, as clusters scatter the microwave background and leave spectral fingerprints. Weak gravitational lensing that distorts galaxy shapes subtly, like a frosted window, letting us map out dark matter distributions without ever touching it. Each of these is a way to convert distance into knowledge, measuring how light from afar is perturbed by what lies in between. The distance between galaxies is a lab bench. Every extra megaparsec is another lens, another absorber, another sheet of structure to read. When surveys stack millions of galaxies, the random orientations cancel, and the residual signal lays down a map of mass on scales we cannot ever visit. On those maps, filaments carry not only galaxies, but also a large fraction of the ordinary matter. Simulations of cold, dark matter cosmologies show why. Dark matter, untroubled by radiation pressure or collisions, collapses early along 3 axes into sheets, filaments, and halos. Baryons fall in behind, shock, cool, and form stars in the knots. The voids are the spaces left between where little collapsed at all. That carving of the universe, if you could look at it in moving coordinates, has been in place since early times, with matter streaming along the filaments into deeper wells. Over billions of years, galaxies migrate down those strands toward clusters, occasionally meeting and merging, getting transformed by tides, having their star formation either quenched by environmental effects or reignited by infall. The distances between the strands themselves expand with the universe. In proper coordinates, filaments are carried apart, their bridges thin out, but locally along a filament, gravity continues its gathering work. That is why you can have both a growing gulf between superclusters and a crowding within a cluster core at the same time. Now, turn your thought to the Hubble sphere again. It is the distance at which the recession speed equals the speed of light right now, roughly CE over H0. It stands at about 14 billion light-years. Because the Hubble parameter h declines in time when matter still matters, the Hubble sphere grows. Photons emitted just beyond it can eventually cross inward as the critical distance recedes past them. That is why the Hubble sphere isn't a prohibitive horizon. The event horizon, by contrast, requires looking to the limit as time goes to infinity and asking whether a light signal emitted at some co-moving coordinate could ever reach us. In a universe with W equals -1, the answer is no, past a fixed co-moving radius that corresponds to about 16 billion light-years in proper distance today. That number is not magic. If dark energy's equation of state is not exactly -1, the horizon would be somewhat different. If dark energy evolves, the future could be wilder. A phantom energy with WW less than -1 would drive an even faster expansion, perhaps a big rip that tears apart bound structures eventually. Current data do not require that. They allow a little wiggle around -1, and most fits hold close. So, when we talk about a 16 giga-year horizon, we do it with an implicit caveat. It's the answer in the simplest case, the one that best explains what we see so far. The way we find ourselves flowing toward the great attractor and its neighbor, the Shapley concentration, illustrates the middle ground between local binding and global dispersal. Peculiar velocity fields show coherent motions over tens of megaparsecs. Matter does not simply sit on co-moving grid lines and wait for scale factors to change. On the contrary, everything we can gravitate toward, we tend to. Our local sheet, a flattened arrangement of nearby galaxies, including ours, sits on the edge of the local void. As that void has emptied further, because underdense regions expand faster than average, its push has contributed to our peculiar velocity. Push is again a misleading word. It's not pressure, but lack of countervailing gravity from the empty side. Imagine a field of masses tugging on you with ropes. If you cut half the ropes on one side, your net acceleration aims toward the side that kept its ropes. The local void is tens of millions of light-years across and largely empty compared to average. The uneven distance to nearby galaxies around its edges tells the story. The expansion is not perfectly uniform when you zoom in, drift a little farther outward, and the fact that voids are worse than you think becomes clearer. The Botez void is a classic, but it is not a one-off. Deep redshift surveys reveal a sponge-like topology where the largest contiguous underdense regions are hundreds of millions of light-years in diameter. Some purported structures, the largest walls and great walls stretching billions of light-years, are scientifically controversial because our statistics on such scales are limited and cosmic variance is strong. The important bit is not which single void is the record holder. It is that, averaged over large volumes, the clumpiness we see is exactly the right amount to match a universe that began nearly smooth, with tiny ripples, and has evolved under the competing rules of gravity and expansion. Voids are natural where the initial wave was below average. Filaments are natural where peaks lined up. The distances between those peaks and troughs grow with the scale factor, but the contrast in density grows too. Voids empty, clusters fatten. In that emptying, we also read the story of time and energy. Photons lose energy to redshift. Each wave is stretched. Each quantum carries a little less punch. Some people ask, is that energy gone forever? And does that violate conservation? In general relativity, energy conservation is subtle when you don't have a single global time-like symmetry to lean on. Locally, in your lab or your solar system, energy momentum is conserved. Globally, in a curved spacetime that evolves, you can't always write a single conserved total energy. So the energy lost by photons to cosmological redshift is not going into a global account you could spend elsewhere. It is a change in how we parameterize light in a dynamical metric. If that feels unsatisfying, it's a fair reaction. Many of the uncomfortable features of cosmology come from applying words that evolved in fixed backgrounds to a fabric that is not fixed. Distance is one of those words. It's why astronomers keep 3 or more definitions in their toolbox and say what distance they mean for each context. Since the topic is distance, ask a sharper question. How many galaxies are near, in the sense that they are reachable for a future civilization with time to burn? Using our event horizon today as the criterion, convert its proper radius into co-moving volume and estimate the number of galaxies inside. A radius of roughly 16 billion light-years corresponds to about 4,900 megaparsecs. Cube that, multiply by 4/3 pi, and you get on the order of 500 billion cubic megaparsecs. If the average co-moving number density of galaxies larger than dwarfs is about 1/100th per cubic megaparsec, a crude number that hides a lot of astrophysical diversity, then the tally inside the event horizon would be on the order of a few billion. Factor in dwarfs, and the number grows. That is the optimistic side of the ledger. Billions of islands within forever's reach. The pessimistic side is another kind of distance entirely. Those billions are scattered across scales where even the nearest leaps would cost tens of millions of years of travel time at fractions of light speed. And most of the cache sits far away and receding. A civilization with great patience could send probes into that pool and wait thousands, millions, or tens of millions of years for returns. The returns would be finite. The pool would not refill with new targets over time. Every billion years, a few more galaxies would slip beyond the event horizon for messages sent then. This is the sense in which the universe is actively making the distance between galaxies worse. Time itself increases the unreachable set. Let's talk about a standard candle that sharpened that revelation. Type 1. A supernovae explode when a white dwarf star in a binary system accumulates enough mass to ignite runaway nuclear fusion of carbon and oxygen. Because the starting conditions are similar, their peak luminosities are comparable after calibration. In the 1990s, teams used these candles to map the distance redshift relation out to redshifts around 0.5 and 1. The result shocked everyone. Distant supernovae were dimmer than they would be if the universe had been decelerating under matter alone since the Big Bang. The inescapable interpretation was that the expansion is accelerating. That discovery earned a Nobel Prize and introduced dark energy into the everyday lexicon of physics. Follow-up work with baryon acoustic oscillations, the cosmic microwave background, large-scale structure growth, and gravitational lensing tightened the case. The cosmology that fits all those data points is flat or nearly flat in geometry overall, with around 30% of the critical density in matter and around 70% in a dark energy component that acts like a cosmological constant. Flatness means the sum of energy densities adds up to a critical value where space is not curved positively or negatively on the largest scales. Matter includes dark matter and baryons. Dark energy is its own, not made of particles we can weigh in a detector. That package is called lambda CDM, lambda for the cosmological constant and CDM for cold dark matter. It is a phenomenological model that does not explain dark energy from first principles. It simply parameterizes it in a way that matches the sky. Within lambda CDM, redshift also tells you something that quietly recalibrates your intuition. Galaxies you see beyond a redshift of around 1.5 R and were receding faster than light at the moment their light left, in the sense of recession speed calculated from the Hubble parameter times proper distance then. That is not a contradiction. The photon emitted then can still make headway because the Hubble parameter decreases in matter-dominated eras, and the Hubble sphere that marks the place where recession equals light speed grows. The light gathers inside the sphere eventually and then piles forward toward you. This is different from the event horizon, which describes what happens in the asymptotic future when dark energy holds sway and the Hubble parameter approaches a constant determined by lambda. In that limit, there is a fixed length scale c over h lambda that never grows past that 16 billion light-year ballpark. Photons from beyond that comoving radius emitted now will never reach us. You can say that galaxies beyond that radius are not part of our future light cone. Every time you stare at the Hubble Ultra-Deep Field or JWST images of early galaxies, you are seeing the stack of those effects. Tiny red dots at Z approximately 10 or higher, their starlight stretched into the infrared, represent systems as they were when the universe was perhaps a few 100 million years old. Their proper distances now are upwards of 30 billion light-years. The look-back times are more than 13 billion years. Whether some of those galaxies are more massive or more luminous than expected at those early times is currently a live area of debate as new data vet old models. But the distances themselves are not in dispute. We are looking across a gulf that is expanding while the light travels. We are looking at places we will never touch, not because our engines are weak, but because the stage keeps lengthening beneath the dancer. Bring this back down to scales that could be measured with a classroom's chalkboard. A megaparsec is about 3.26 million light-years. Hubble's law says that for each megaparsec of proper distance between non-bound systems, you add about 70 kilometers per second of recession today. A galaxy 10 megaparsecs away, 700 kilometers per second. 50 megaparsecs, 3,500 kilometers per second. 100, 7,000. By the time you are 4,000 megaparsecs out, about the radius of the event horizon in megaparsecs, the recession speed approaches the speed of light. That quick scaling gives you a visceral sense of why local and cosmic play by different rules. The Milky Way feels nothing of that. Even the local group as a whole is insensitive. But as soon as you're mapping clusters and superclusters, you must use at least two clocks. A local one, where velocities and potentials work mostly like Newton taught us, and a cosmic one, where the metric evolves and the rules forbid certain types of causation. When we say dark energy is not a wind, we should also say what we mean by its pressure. In general relativity, pressure contributes to gravity the same way energy density does. Ordinary matter has positive pressure in most settings. Dark energy with WW approximately equals -1 has negative pressure of the same magnitude as its energy density. That negative pressure gives it the property of accelerating the expansion. If you want a metaphor, think of stretching a rubber sheet where the sheet's tension grows as it stretches. That's just a metaphor. The equations say, in a Friedmann-Lemaitre-Robertson-Walker spacetime, the acceleration of the scale factor depends on energy density plus 3 times pressure, in units where c equals 1. If that sum becomes negative, meaning pressure is sufficiently negative, then the second derivative of the scale factor is positive, acceleration. The microscopic origin is a mystery. A vacuum energy from quantum fields is a candidate, but naive calculations of its value overshoot the observed dark energy by mind-bending factors. That mismatch is a clue or a challenge, depending on your taste. Because distance and time are braided together, the worse than you think story also includes a trap in language for early learners. People sometimes imagine that galaxies are dots flying away through empty space as gunshots towards targets. But galaxies are more like dust motes in rising bread dough. The dough doesn't push the motes. It defines distances with a scale that grows. Dots do move relative to dough because of local currents, peculiar velocities, but on average, a pair of dots on the unbound part of the dough will find their separation per unit time proportional to their distance. Nearby pairs separate more slowly, far pairs separate more fast. This is not because of interactions between the dots, it is because of the way the distance is defined. Everything I'm describing happens against a background of light we can translate into concrete measurements. Do you want to know how far Andromeda is, not just as a round number, but as a carefully measured distance? Astronomers anchor it with Cepheid variables observed by Hubble, with detached eclipsing binaries that let you derive precise distances from orbital dynamics and luminosity. With red giant's tips and with geometric maser disks in other galaxies that calibrate the latter. We know Andromeda's distance today is roughly 2.5 million light-years with small error bars, and its approach speed is about 110 kilometers per second toward us, visible in the blue shift of its spectrum. That's a case where recession does not apply. Now jump out to Virgo, measure its distance with surface brightness fluctuations, supernovae, and the Tully-Fisher relation across numerous member galaxies. Average those and you get around 16.5 megaparsecs. Its mean redshift corresponds to a recessional velocity of a little over 1,000 kilometers per second after removing our peculiar motion. That is a case where recession does apply, with a dollop of local flow on top. Every rung up in distance begs a more general description of motion and asks you to keep careful track of frames. Frames matter because when you say a galaxy is now 10 billion light-years away, that now is in our cosmic time, defined by the rest frame of the cosmic microwave background. Within that frame, simultaneity has meaning for cosmology, even though relativity somewhere else seems to outlaw absolute simultaneity. We can define cosmic time slices where the universe looks homogeneous and isotropic on large scales. Proper distance now is measured along those slices. Look-back time tells you how long the light has traveled between different slices. You can imagine the universe as a stack of snapshots at different scale factors. We live on one snapshot. We look back through the stack with a finite cone of light. We cannot look ahead through it. That alone makes the word distance something like a walking stick in fog. It keeps you stable, but it doesn't change the fog. Another way to grasp how bad is bad is to take a virtual tour across scales and keep a running count of emptiness. Start in the solar neighborhood, a few light years from the nearest star. Jump to the width of the Milky Way, 100,000 light years. Multiply by 25 to get to Andromeda. Multiply by another 20 to get the base of the local group. Multiply by 20 again to reach Virgo. Multiply by 2 to cross the local supercluster's nearest wall. And then multiply by hundreds to get to the scale of the Botez void. The number of molecules in a breath of air is larger than the number of galaxies in the observable universe. The number of cubic light-years in the Botez void is so huge that even if there were a million dwarf galaxies adrift within it, you could travel for tens of millions of years between any two without brushing a star. This is the face of what we call empty. The intergalactic medium in a filament might have 1 atom per cubic meter. the void could have far fewer. If a human being stood in true deep cosmic space unprotected, if we ignore the lethal physics of such a stunt, they would be at the lonely edge of what any animal could mean by wilderness. And yet, the arithmetic of gravity means that even small differences in that emptiness matter. A filament with a slightly greater overdensity attracts more flow. A void with a slightly more severe underdensity expands faster. Gravity is patient. Given time, it will accentuate what is there. But dark energy is patient in another way. Given time, it will dilute the very theatre in which gravity plays. It will not unbind clusters. Those are held in their own pockets of curved space. But it will lower the background relevance of farther masses to each other. In the far future, every filament will be surrounded by more nothing in the proper distance sense than your intuition will accept. The cosmic web skeleton does not unwind, but the spaces between its bones widen tremendously. Let's follow a few narrow threads to anchor these abstractions. The coma cluster is about 100 megaparsecs away, translating to roughly 330 million light-years. It contains thousands of galaxies and a deep potential well filled with X-ray emitting gas. Its richness exceeds Virgo's. Its recessional velocity is around 7,000 kilometers per second in our frame. Seeing it tells us about distance, the same way looking at tree rings tells us about past droughts. The galaxies in coma are on average older looking than field galaxies at the same redshift, quenched, elliptical, having turned their gas into stars long ago. The distance across coma's core is a few megaparsecs. Even there, with galaxies packed denser than the field by factors of 100 or more, space is mostly vacuum. The freefall time from coma's outskirts into its core is on the order of billions of years. That is honest to goodness long. If you drop a marble in a bowl and it takes 1 billion years to roll to the center, that tells you something about the depth and width of the bowl. Coma's distances give a tactile sense. Gravity is doing what it can, but the cosmic time budget is measured in eons. Consider also the local void's tug on our motion. The local sheet's galaxies share a bulk flow of a few hundred kilometers per second relative to the CMB rest frame. Part of that flow is toward Virgo, part is away from the local void. Observationally, we reconstruct this by measuring distances to many nearby galaxies, subtracting the Hubble flow, and mapping residual velocities. The edges of voids show galaxies with peculiar velocities pointing outward from the void center. Over the last few billion years, as dark energy started accelerating the background expansion, voids gained ground in relative size because matter wasn't streaming into them. There was nothing to stop them from expanding faster than the mean. Distances between void walls grew faster than in denser regions. The cosmic web amplified its own contrast. Distance is data, but it is also perspective. When astronomers first measured the Andromeda Nebula's velocity and found it approaching, they realized nebulae were not just clouds within the Milky Way. When Hubble and Lemaitre related redshift and distance for many such nebulae, the universe grew in our minds. Then, the microwave background was discovered, and the scale of early distances was set by a single canvas. Today, with deep surveys revealing serendipitous alignments and surprises, giant arcs from gravitational lensing by clusters bending background galaxies into smears and rings, we see distance as a lens maker. A foreground cluster a few billion light-years away can magnify a galaxy 12 billion light-years off. Strong lensing adds image multiples with delays in the light paths. Measure those delays. combine with models of the mass distribution, and you derive h0 independently. Another rung, another chance to test whether the distance-redshift relation hangs together across techniques. When it does, the overall picture of an expanding universe is overdetermined. It's not one fragile inference, it's many mutually supportive inferences. That allows us to be bolder when we make claims about event horizons and far futures, even though we have never waited 100 billion years to check. Let's spend a moment on the shapes of walls and the distances that define them. The Sloan Great Wall is a chain of galaxy clusters and filaments about 400 to 500 million light-years long in comoving length. It is not a single monolithic object, just a contiguous overdensity. Even such a stupendous string is a small fraction of the observable universe's width. It's like a vein on a leaf compared to the forest. Beyond Sloan, claims of even larger walls, or great walls, run up against sample size and the human tendency to see patterns. Reliable structures on scales of a few hundred megaparsecs are expected. Larger than that, and luck can look like law. Regardless, these walls are not walls in the way a city has walls. They are bumpy cauldrons where galaxies stir, separated by rooms where galaxies are rare. The distance between one wall and the next is a measure of how the early density field chose to lay itself out. What about the distances to the earliest lights we can see, and how those lights have been reinterpreted as telescopes improved? The James Webb Space Telescope has pushed our detection of candidate galaxies to redshifts above 10 and even 13, if some photometric estimates hold up spectroscopically. At zeta equals 10, the universe was 1/11th its current size. The look-back time is about 13.3 billion years. The proper distance now to a galaxy at that redshift is around 31 billion light-years. Again, we can see it because its light left long ago, when the proper distance was smaller. We cannot touch it now or ever. The distance between galaxies at that time, what average separation meant then, was smaller because the scale factor was smaller. But the comoving distance between the seeds of what would become those galaxies and the Milky Way's progenitors is the same today as then, by definition. The fossils of those distances are stored in the microwave backgrounds anisotropies and in the statistical correlation of galaxy positions in the modern universe. We learned to freeze the movie at different frames and count. Then we learned to rewind and fast-forward the movie with simulations and compare the counts. No distant story is complete without talking about light travel time illusions. When a distant galaxy's supernova explodes, we see it when the light arrives. If that galaxy is 10 billion light-years away in look-back time, then we are seeing it as it was 10 billion years in the past. Between then and now, the galaxy has evolved. It may have merged. It may have quenched star formation. It may have spun down and up in some internal mode. Our picture is a palimpsest of snapshots spread across cosmic time. That is why the distance between galaxies can't be a single number. The nearest big neighbor has one value. The typical neighbor in a cluster has another. The galaxy we can see at the edge of detectability has a proper distance now much larger than its look-back time would suggest. And the set of galaxies we can talk to at all is smaller than the set we can see. That last sentence is the curveball. Even as your telescope grows and you aim deeper, like a sailor seeing new islands as you climb higher in the rigging, the map of islands you can dock at does not grow past the event horizon. Not in the long run. That long run invites one more calculation. How quickly does the night sky thin? It isn't that galaxies will suddenly blink out. Their light will keep arriving, redder and fainter with each passing billion years. The near edge will remain crisp. The local group's lights will burn for trillions of years in faint red embers of small, long-lived stars after star formation stops. But the far edge will erode in a continuous way. Galaxies now at Z, approximately 1, will remain visible for a very long time. Galaxies out at Z, approximately 3, whose present proper distance is around 20 billion light-years, will drift past the event horizon for new signals fairly soon. In cosmic terms, after a few tens of billions of years, the visible universe will be reduced to a bubble around each gravitationally bound structure. The cosmic microwave background will be stretched to wavelengths larger than meters, then kilometers, then astronomical units, then light years, numbers where detectors built from matter become functionally unable to sense them. It takes optimism to imagine a device that can pull a coherent signal out of a wavelength longer than your galaxy. At some point, the background will be functionally gone. Distance is not a doom. It is a parameter we can tame with clarity. Knowing that dark energy exists tells us exactly what to look for in the shapes of the distance redshift plot. Knowing that our local group is bound tells us what to expect from the future of our star field. Knowing that voids grow helps us understand our own motion through space. The local sheet's speed of a few hundred kilometers per second relative to the CMB dipole is a direct hint that we live on the edge of emptiness. Each such fact folds into a story where galaxies are rarer than our pictures suggest, and the space between is not simply in the way, but is the main event. If this begins to feel isolating, return to the practical. The galaxy count inside our event horizon is enormous compared to the scale of human projects. If a civilization ever masters the patient art of sending autonomous probes at a significant fraction of light speed, the reachable domain is not a tiny handful. It is a sphere containing billions of separate targets. The tragedy is not that there is nowhere to go. The tragedy, that might also be a kind of mercy, is that there are more places than time to go, and that our maps will never be complete no matter how long we survive. You can turn that into a scientific strategy instead of a lament. We survey statistically, we sample cleverly, we take advantage of lensing magnification when the universe gives it, and we accept that we will always be interpreting a finite set of clues about an infinite set of events. What of the word worse in the title you clicked? It was a hook to the idea that distance in cosmology is slippery. It is worse because it multiplies meanings. It is worse because it hides causal boundaries in a sky that looks continuous. It is worse because the universe accelerates, carving an event horizon into our future that no engine can cross with a message. But worse does not always mean darker. In a different sense, the distances are better than you think. They are the ruler by which we have learned what little we know about everything, from the temperature of the background, to the growth of structure, to the era when the first stars flickered on. They are why we can say, the local group, and mean a parcel of space we will keep. They are why we can say Virgo, and know that although it recedes, it is an empire in its own right, whose gravity will hold its cities together for far longer than Earth has been a planet. They are why we can draw a line 46 billion light-years long and say, within this, the universe has had time to speak to us. And they are why we can draw a line 16 billion light-years long and admit, beyond this, our voice will not carry. If the distance between galaxies is worse than you think, it is also the shape of our luck that we live early, that we can see so much, that our instruments still drink from a river of light wide enough to reveal a web of superclusters and voids and embryonic galaxies. Early astronomers looked up and could hardly imagine what the nebulae were. We look up and can hardly imagine what our sky will look like to minds 100 billion years from now. Skies dominated by a single giant elliptical and a sea of red dwarfs. No whisper of a microwave afterglow, and no galaxy beyond the local island to betray that there was ever a universe beyond. They will find their own evidence, perhaps buried in primordial isotopes or gravitational wave backgrounds. But the view we have now is privileged. That privilege is a responsibility. We capture as much as we can while we can, knowing that our archives may be the only record some future intelligence has of the broader cosmos. The last line in this story reaches back to the first. The distance between galaxies is not a fixed scar on space. It is a moving boundary between what is together and what is apart, between what can still be in conversation and what is already ghosted by time. We began with the claim that it is worse than you think because it is dynamic, stretched by dark energy, shaped by voids. The fresh insight at the end is that this bad news is our best map. It tells us where to look, what to expect, what we will never touch, and what we can still save from fading away. The gulf is growing, the web is thinning, but for the moment, the universe is still close enough to hear. Close enough to hear means close enough that a reply is still possible. That is the key asymmetry the expanding universe creates. We can receive news from almost everywhere we can see, but only a subset of those places can ever hear back from us if we tried to speak. If you pick a galaxy on the sky at random, its photons can in principle reach our detectors given enough patience. Those are lines of sight that enter our past light cone. But draw the complementary shape, the region of space that a message we send now can ever reach. That forward reach is bounded. Some galaxies we are watching are already outside of it. Their light will continue to arrive, older and more stretched, but nothing we do can propagate influence in their direction that arrives in finite time. The universe, with dark energy in charge, splits sight from touch. Causal boundaries in cosmology come in several flavors, and the words can sound like a tangle until you tie each to a question. The particle horizon asks, how far away could light have traveled to us since the hot beginning? The answer, today, is on the order of 46 billion light-years in proper distance, a limit set by the age of the universe and the cumulative stretch of space along the entire history of the light's journey. That is the edge of what can have signaled us by now if it emitted flashes all along. The event horizon asks a different question. What is the farthest place at which an event anyone performs today could ever, in principle, influence what we will see? In a universe whose expansion is accelerating toward a de Sitter-like state, that horizon is finite and sits, for us, at roughly 16 billion light-years in proper distance. Anything happening beyond that proper distance right now is forever out of conversational range. The Hubble sphere, by contrast, is just the distance where recessional velocity from expansion equals the speed of light at this instant, about 14 billion light-years. But that is not a hard causal limit, because space can speed light up or slow it down relative to that sphere as the expansion rate changes. It is a diagnostic, not a fence. There is also an apparent horizon, the place in a cosmological spacetime where null geodesics turn from converging to diverging. For an accelerating universe, this tends to line up with the event horizon. Each horizon answers a different "can I know?" or "can I influence?" question. Together they sketch our causal diamond, what we can ever see and what we can ever touch. These horizons are not walls. You will not hit them with a probe or see a line in the sky. They are paths in space-time, traced by light itself. They are best pictured as slopes in a graph of time versus co-moving distance. If you fix a galaxy at some co-moving coordinate, meaning it rides the overall expansion, its world line is a vertical line on that diagram. Our past light cone is a slanted line approaching it. If the world line sits far enough to the right, our light cone never intersects it in the future. That is what "can never talk to" looks like in the calculus of causality. And that picture also lets you ask more precise questions than near and far. For example, if a civilization in a galaxy 20 billion light years in proper distance sends out a message right now, it could still be that we never receive it. Not because the message cannot travel at light speed, but because the space between is lengthening in such a way that the null path never intersects our world line. Light obeys local rules. The geometry writes the plot. Signals themselves carry the signature of this plot. Think of a beacon in a receding galaxy that pulses in a metronomic rhythm, a standard clock in the sky. Its pulses reach us not at the original cadence, but stretched in time by the same factor that stretches their wavelengths. An event that took 1 second between bombs in that distant ship's engine room can arrive spaced by tens of seconds, then hundreds, then years, as we watch it ever farther down the recessional river. That time stretch, the cosmological time dilation, is not a nuisance. It is a measurement. We have seen it in the light curves of Type 1. A supernovae. Explosions in galaxies at redshift z equals 1 are slowed by a factor of 2 in our frame, as every tick of the explosion's physics is spread out by expansion. That factor is exactly 1 plus z. It is a direct, clean sign that redshift is not a tired light effect, but a kinematic stretching of spacetime itself. And it is one reason light from beyond our event horizon gets weird in the limit. If you watch an emitter whose world line asymptotically slides behind the horizon, there is a last photon from that source you will ever receive. It is not that the source stops radiating. It is that each subsequent pulse runs out of road to cross. The final one arrives infinitely red, infinitely late. The converse is something subtle. Redshift itself is not fixed. It drifts. A distant galaxy's spectrum, if we could hold a perfect stable instrument on it for a few human lifetimes, will shift measurably in wavelength even if the galaxy isn't moving with respect to its comoving patch. This is the Sandage lobe signal, the redshift drift. In an accelerating universe, low redshift galaxies should very slowly drift to lower redshift, as if creeping toward us at a few centimeters per second over decades. High redshift galaxies should drift to higher redshift, as if slipping away faster. The change is tiny, centimeter per second tiny, and hard to catch, but not forever out of reach. Next generation ultra-stable spectrographs and 30 to 40 meter class telescopes will try to feel that pull. Why bother with such a small effect? Because it is a measurement of expansion that does not lean on standard candles or rulers or complicated astrophysics. It is, in a very pure sense, watching the scale factor change in real time. A direct confirmation that the universe accelerates is collected not only from triangles worked out in redshift distance plots, but from the steady creep of lines in the Lyman alpha forest. Now consider what it means to send, not receive. The practical limit of our reach is set by the event horizon. In proper distance and proper now, pinned to our cosmic time slice, that is around 16 billion light-years. But our sending ability depends not just on where the boundary is now, but when we send. If you launch a signal later, from a later, faster expanding epoch, the reachable co-moving volume shrinks. A message sent today has more reach than the same message sent in 1 trillion years. There is an urgency baked into the geometry. In terms of co-moving coordinates, the event horizon defines a maximum co-moving radius, r sub e, such that light rays launched from us now asymptote to that r sub e. The longer you wait, the smaller the co-moving ball you can ever affect. This is not a human-scale warning. No one is urging you to fire a probe before lunch, but as a cosmic scale statement, it is a kind of arrow in time. Local actions lose their leverage as the cosmological constant takes over. Some of those subtleties matter even for near-term science. When we talk about reachable, we tend to mean send a probe. But even receiving is dynamic. Galaxies that are technically still inside our event horizon will, for practical astronomers, 100 billion years hence, have faded to invisibility, not because the geometry forbids reception, but because reception becomes meaningless when the signal's photons are redshifted below any reasonable detector bandwidth. There are physical detectors that could, in principle, match the stretch. Gigantic antennas or exotic plasmas with astronomical coherence lengths. But actual matter at finite temperature produces noise, and the horizon's own de Sitter temperature is not zero. In a vacuum dominated by dark energy, the horizon bath glows faintly with a Gibbons-Hawking radiation field with an absurdly low temperature, about 10 to the power of minus 30 Kelvin. That bath, irrelevant now, sets a floor under detectability across extreme timescales. Make a receiving array the size of a galaxy, and the horizon whispers louder. The word horizon carries a whiff of despair that is too heavy for what astronomers do with it. Horizons let us compute. They let us say what we can bet on and what bets are meaningless. They also let us partition the future into pieces with different destinies. The local group's fate, for instance, is not to be smoothed away. It is to become more itself. The Milky Way and Andromeda will merge in roughly 4 to 5 billion years, give or take pendulum swings of gravity amplified by their halos and satellites. Triangulum will be entangled. The result will be a massive, slowly rotating or gently triaxial system, with most of its new stars forming out of the gas funneled in by tidal tails and halo cooling. The details depend on the initial angle of approach, the density of their circumgalactic media, and the orbits of their companions. But some generalities are hard to escape. The supermassive black holes at their centers will spiral in and coalesce, radiating gravitational waves with periods of hours to days at the end. A seismic tremor in space-time that instruments like pulsar timing arrays would have heard if they had been around then. The final black hole's mass will be about the sum minus whatever energy is blasted out as waves. Angular momentum will be shed and the core will settle. Star formation will spike during the merger, and then cut off from fresh cosmic inflow by the widening emptiness between groups, ebb. Gas that is not consumed will be heated by accretion onto the central hole, and by supernova, buoyed into a hot X-ray bright halo where it may linger for gigayears, cooling only in filaments that fall back like rain. Over time, longer than the Earth has until the Sun's own metamorphosis, the merged galaxy will use up, heat, and recycle its gas until the easy stars have been made and the difficult ones are starved. What remains are red dwarfs and embers, and star formation that carries on, if at all, in slow-motion drips that stretch across trillions of years. The starfield we bequeath to those far future nights is not black. It is just older, quieter, a different distribution of lifetimes. In parallel, everything not bound to the local group will continue to slide out of causal contact. Virgo, bright on our current sky as a rich cluster, will eventually be so far away in proper distance that a single galaxy, our merged remnant, will see it no longer as a set of neighbours but as a piece of the external backdrop that never changes because no fresh light arrives. Its internal ballet, galaxy collisions, central flares, turbulent gas, will continue, but their updates will never refresh our screens. Inside Virgo, gravity remains king. Outside in the spaces between bound structures, dark energy becomes an ever more dominant choreographer. You might ask whether mass that is already out past the event horizon still tugs on us. Gravity, in general relativity, is not a force that reaches in instantaneously from distances. It is a curvature of space-time itself, and its changes propagate at light speed. The large-scale influence of mass energy beyond our event horizon is part of the overall FRW geometry we inhabit, baked into our decelerations and accelerations from the earliest times. New changes, someone moving a planet in a galaxy beyond the horizon, cannot reach us. The background potential from super-horizon modes is not felt as an extra push today. It is felt as the background we already live in. Within that, the local group decouples, not because gravity punches through horizons, but because its self-gravity dominates local curvature. The separation between visible and reachable astronomies shapes how we think about discovery. Photons give us information backwards in time. Messengers like neutrinos and gravitational waves do as well. Each has its own horizon, not only in a geometric sense, but in an opacity sense, when the early universe became transparent to them. Photons were last scattered at a redshift of about 1,100, when electrons and protons combined to form neutral hydrogen. That is why the cosmic microwave background is a surface, not a volume. Neutrinos decoupled much earlier, about 1 second after the Big Bang, at temperatures of a few mega-electron volts, and they form a relic background that floods space even now. In principle, a civilization that could detect the cosmic neutrino background would see deeper, to an earlier horizon. But the practical difficulties are enormous. Neutrinos barely interact, and their energy today is so low that building a detector that can feel them without being overwhelmed by everything else seems beyond any reasonable engineering. Gravitational waves decouple at the very beginning, effectively at the Planck time, if what we mean by waves remains sensible there. Their background, if measurable, would be a probe of inflation or whatever replaced it. Yet even for gravitational waves, redshift makes the early signal super low frequency, longer than a galaxy, and shorter wavelength backgrounds get drowned by astrophysical sources. Light remains our workhorse. Redshift-based astronomy, turning photon frequencies into distances and times, works not because everything we see is simple, but because the ensemble statistics obey simple rules. Standard candles like type 1. A supernovae give us luminosity distances. Standard rulers, like baryon acoustic oscillations, give us angular diameter distances, and the reciprocity between them, the distance duality relation, holds in any metric theory with photon number conservation. That relation, luminosity distance equals angular diameter distance times 1 plus z squared, has become a diagnostic in itself. If we ever measured a deviation that could not be explained by grey dust or selection effects, it would hint at exotic physics, photon, axion mixing that steals photons into the dark sector, or something stranger. So even the limits of redshift astronomy feed back into discovery. When theory tells us distances must obey a reciprocity, any observed betrayal is a clue. Standard rulers do more than set a scale. The acoustic peak in the correlation function of galaxies, a blurred echo of pressure waves in the baryon photon fluid before recombination, sits at about 150 megaparsecs in co-moving units. Measure that feature along and across the line of sight at different redshifts, and you get h of z and d sub a of z separately. One tells you how fast cosmic time pours out along our line of sight. The other, how angles project on the sky. Combine that with redshift space distortions, the fingers of God that show velocity dispersions in clusters, and the Kaiser squashing that shows coherent infall on large scales, and you have a way to weigh growth. Gravity pulls structures together. If the pull is stronger or weaker than general relativity predicts, or if dark energy does more than simply curve the background, those redshift space maps will tell on it. That is the other power of distance. It lets us test the rules, not just draw a map. Gravitational lensing is part of the same story and extends it. The way distant galaxies are sheared weakly by intervening mass, the tiny, coherent alignments called cosmic shear, depends on the geometry between us, the lenses, and the sources. It also depends on how clumpy the mass is. Precision cosmology uses this double sensitivity to both distances and growth to break degeneracies. A universe with a slightly different Hubble constant and a different matter density could reproduce the same supernova Hubble diagram. Lensing helps tell which solution is true. So does the cosmic microwave background. Its pattern of peaks and troughs are an exquisitely calibrated photograph of the universe when it was about 380,000 years old, with a preferred angular scale that, once projected through intervening expansion, sets an overall distance ruler. When we say the cosmic distance redshift relation hangs together across techniques, this tapestry is what we mean. Candles, rulers, shears, and the CMB all weave a consistent shape when you pick the right parameters. Those parameters are not just H0 and omega m. We ask the data to tell us whether space is flat or curved on large scales, whether dark energy's pressure to density ratio, W, is exactly -1 as a pure cosmological constant would be, or slightly different and perhaps changing with time. We ask whether gravity itself behaves differently on scales of hundreds of megaparsecs. Distances are where those questions meet observation. The one thing distance measurements do not do by themselves is free us from modelling. Every distance we infer from fluxes or angles flows through assumptions about dust and metallicity in supernova hosts, about the stellar population synthesis in luminous red galaxies we use to trace BAO, about instrument calibration. Redshift is a clean observable. Turning it into geometry tests our ability to model the messy universe we actually see. That is why limits of redshift astronomy is not an apology. It's a budget, a list of line items we can invest in. Better photometric redshift training sets for deep surveys reduce catastrophic outliers in weak lensing tomography. Cross-correlating intensity maps, summed emission in a line like CO or C2 without resolving individual galaxies, with optical galaxy surveys peels apart the interloper lines that masquerade at the same observed frequency. Forward modeling selection functions in full 3-dimensional mock surveys reduces Malmquist bias. None of this is cosmic poetry. It's engineering our way to better use a cosmos that will not wait forever. A piece of that engineering is simply going wider and longer. The sky that looks uniform to your eyes is marbled with structures that take statistical heft to measure. Cosmic variance, the fact that any particular patch of sky could be unrepresentative just by luck, goes down as you sample more sky. Deep fields give you then, wide fields give you on average. Time domain surveys, revisiting the same fields for years, build something different. An ability to see subtle drifts and to catch transients that can be used as rulers and clocks. The hope that we will measure redshift drift with telescopes like the ELT rests on that philosophy. Narrow your gaze to a set of quasars with rich Lyman alpha forests and watch patiently as the absorption lines creep. The signal is so tiny that it will take decades of data to rise above instrument jitter and atmospheric noise. But decades are a reasonable investment when you weigh them against the billions of years that will, eventually, erase the sky's evidence of acceleration. We measure the acceleration now, in the only era when many independent methods are possible, precisely because future astronomers will not have this luxury. There are other instruments in our quiver that are young but promising. Gravitational wave detectors turn some mergers into standard sirens. The chirp of a binary neutron star spiraling together encodes the absolute luminosity distance directly in its amplitude when you understand the general relativity that governs the waveform. If you also know the redshift, by identifying the host galaxy in light, or statistically by cross-correlating with a redshift survey, you have one more node on the Hubble diagram, free from the atmospheres of supernovae and their environmental quirks. As networks of gravitational wave detectors grow more sensitive, and as space-based observatories like LISA come online to catch supermassive black hole mergers at redshifts of a few, we will have rulers that cross-check the luminous and the dark. Each such check squeezes the error bars on W and brings us closer to declaring whether dark energy is a simple cosmological constant or a field with dynamics. Behind the spectroscopy, there are practical hurdles that do not make feature reels, but matter enormously. K-corrections, the transformations needed to compare a galaxy's brightness measured in one band at one redshift to another's at a different band and redshift, depend on a galaxy's spectral energy distribution, which itself evolves with star formation, history, and dust. Mismodeling those corrections can bias distances. So can Eddington bias, where scatter in an intrinsic property combined with a steep luminosity function inflates the counts of bright objects preferentially. Photometric redshifts, essential for billion galaxy weak lensing surveys, are trained on spectroscopic samples that are brighter and bluer than the full set. Extrapolation errors can creep in. Lensing itself magnifies and demagnifies sources, warping number counts and skewing flux-limited samples. Every one of these effects, if uncorrected, causes a tiny tilt in the distance redshift relation. Accumulated across millions of galaxies, tiny tilts move cosmological inferences. That is why the field leans so hard on simulations that grow galaxies in boxes with the right physics and then observe those boxes with virtual telescopes to check for biases before they matter. There is also the mundane challenge of dust between us and everything. Intergalactic dust is not abundant, but even thin veils can add extraneous dimming and reddening that mimic distance. We check against that with color information, polarization, and spectral features. We also exploit something more global. The Tolman surface brightness test predicts how the surface brightness of identical objects fades with redshift if the universe expands, as 1 plus z to the power of 4. This is not a small effect. Observations across a range of redshifts confirm the predicted dimming. Another signal that the redshift we measure is not a trick of photons losing energy somewhere in flight. Putting that together with time dilation in supernovae builds a case. The distances we calculate are not artifice. They are consequences of space-time stretch. Even with those strengths, there are natural limits. There is a redshift desert in spectroscopy, a range where convenient emission lines shift out of optical bands into parts of the infrared that are challenging from the ground, and where lines can be faint. JWST and other infrared-capable telescopes are filling that gap, but not for everything, everywhere. At very high redshifts, the Lyman alpha line, the hallmark of star-forming galaxies, runs into a fog of neutral hydrogen before ionization, damping it out. The Gunn-Peterson trough appears, a blacked-out forest in a quasar's spectrum where there is simply no transmission. That too is a distance measurement of sorts. The shape of the trough's edge tells you the timing and patchiness of reionization. It is the first light frontier turned into an absorption experiment. Going even earlier, to cosmic dawn, we trade starlight for the 21-centimeter spin-flip emission of neutral hydrogen. Instruments like HERA and the future SKA attempt to map the three-dimensional distribution of that line as it redshifts from hundreds of megahertz to tens, tracking bubbles of ionization around the first galaxies. It is a different kind of cartography, intensity mapping rather than resolved galaxy counts, but the result is against a ladder of distances, how angular features of known physical scale project at different redshifts. The reason to go to that trouble is not just curiosity about first stars. Those 21-centimeter maps, in principle, can be cross-correlated with CMB lensing maps and galaxy surveys to isolate cosmological signals from astrophysical contamination. Each cross-correlation carves out otherwise hidden systematics. More precise distances at high redshift close a loop. Calibrate dark energy at late times using supernovae and BAO, and tie that calibration to an early time anchor set by the CMB and 21-centimeter BAO. A consistent story across those extremes stiffens our confidence in the extrapolation we make when we talk about event horizons and ultimate fates. There is a conceptual leap here we can make safely. The future will not invent a new geometry inside our causal patch. Local physics can surprise us, new forces, new particles, but the global structure of our causal diamond is set once we fix the large-scale parameters of expansion. That means that the fates we sketch, what we keep, what we lose, are conditional only on whether dark energy behaves as it appears to now. Suppose it does. Then the local group's isolation will be not just perceptual but functional. Gas inflows from the cosmic web, which now feed galaxies and send cold rivers of fuel down their potential wells, will be cut off. The intergroup medium will thin and cool. Interloping dwarfs will be shaved away or captured, adding to the stellar halo. The central black hole may enter cycles of activity as it feeds sporadically on those dwarfs and their gas. There is an irony in this. Activity in our sky will, on the scales we care about emotionally, night skies, starbirth regions we could photograph, be dominated by very local events at the same time that the global sky drains away. The distance we feel in our bones at that time will be to the next star, not the next cluster. That distance will be measurable and important for travel, even when the word Virgo has lost its practical meaning. The difference between visible and reachable is not only relevant to astronomy. It defines the philosophy of exploration for any civilization. How do you deploy probes and ambitions, knowing that some targets you can see are pointless to aim at, because no craft moving below light speed will arrive with fuel in the tank and time left in the universe? You pick your net based on the event horizon, not the particle horizon. You prefer strategies that trade long, fragile chains of resupply for self-contained autonomy. You might seed self-replicating machines within the bound domain, building a network that can endure for eons, even as the sky of possible correspondence shrinks. That is a sober reading of distance. The optimistic reading is that the set of reachable galaxies, measured in the billions, is more than enough for projects that stretch any reasonable definition of civilization. The tragedy of horizons is an ethical question only when you imagine someone left out there who needed help. In the cosmos we actually inhabit, the moral is narrower. Local stewardship is our leverage. Archival stewardship is our gift. Back to the measurable. Distances help us decide whether we are missing something in the budget. There is a persistent tension in the value of the Hubble constant, measured by local distance ladders and by early universe inferences from the CMB and BAO. A numerical dissonance that could be calibration error, or could be the first tickle of new physics. New rungs like the gravitational wave sirens and strong lensing time delays are part of how we adjudicate. The latter uses a shortcut that feels like cheating but is pure general relativity. A quasar lensed by a galaxy can produce multiple images with different path lengths. As the quasar flickers, the echoes between images measure those path differences directly. Turn the delays and the shape of the lens potential into a time-delayed distance, and you have another point in the distance-redshift relation. The devil is in the mass model. Mass sheet degeneracies in lens models can bias distances. But we are not helpless. Stellar kinematics in the lens galaxy and the shape of extended arcs help pin down the mass distribution. Each improvement turns what used to be a curiosity into a cosmological tool. There is also a way to measure h of z that barely mentions light curves or lens models. Cosmic chronometers. Massive, passively evolving galaxies hold a record of time in the shape of their stellar populations. Compare the ages of such galaxies at two redshifts that are close to each other, and you can estimate dz over dt, which is proportional to h of z. The uncertainties are real. Stellar ages depend on the assumed star formation, histories, and metallicities, but the method is different enough in systematics that it triangulates. The more orthogonal our methods, the safer our inferences. That is the quiet power of distances. They are so connected to everything else, growth, geometry, physics, that many independent paths lead to the same hilltop. We have dwelt on photons because they are our lifeblood, but their stories are laced with small traps that can seduce the unwary. Take, for instance, selection by line. At high redshift, a galaxy can appear red not because of age but because of dust, or because a strong emission line is enhancing one photometric band. Photometric dropout surveys that identify Lyman break galaxies by their absence in one filter and presence in another can be fooled by lower redshift interlopers with the right mix of lines. That is why photometric claims of extremely high redshift objects become robust, not when they sit alone in a catalogue, but when they appear in the right number, densities and environments. with the right lensing magnifications where lensing is present, and when spectra show the telltale damping wing of Lyman alpha cut off by a neutral, IgM. Distance is not one measurement. It is a verdict from a jury of measurements, all with their own priors and prejudices. The picture we have assembled of horizons and lensed rulers and drifts of lines measured by telescopes yet to be built could feel abstract without anchoring it to an explicit future for our sky. So, draw it. In the near term, tens of billions of years, the map of reachable galaxies will stabilize, not because galaxies stop, but because the geometry freezes their accessibility. The local group will have one deep potential well, the nearest clusters now beyond the local group, Virgo, Fornax, will recede to such distances that only the afterglows of their brightest pasts remain in our archives. The intragroup medium will cool. Stars that remain will be long-lived. The cosmic microwave background will pass through meter wavelengths and then beyond, not just redder, but colder in its detectable energy density at frequencies where instrumentation hits quantum and thermal flaws. The dipole we measure now in the CMB, a sign of our motion relative to the cosmic rest frame, will be unmeasurable without the background itself. The concept of a cosmic rest frame will become philosophical instead of practical. Stretch farther into the trillion-year future and the details get speculative because particle physics intrudes. If protons decay, the ultimate chemical inventory will change. If dark matter decays, halos will lighten. If neither decays, the universe will be a museum of degenerate remnants, with black holes dominating the mass budget inside bound structures. None of those downstream possibilities change the causal structure. Distances keep their teeth. The horizon will still define what can be known by fresh light. The remnants of what we learn now will still be valid within our causal diamond. That may be the deepest comfort this science offers. The things we figure out about distances are durable, immunized against future erasures, because they are statements about invariance. We can turn that into a responsibility, almost literally. Our telescopes, especially space telescopes, are not just instruments for papers. They are machines that can make a record. Astronomy has always been cumulative, but in this era it becomes archival in a more permanent sense. Spectra stored with the calibration files and instrument metrology and pointing histories included. Imaging stored with the masks of bad pixels and the point spread functions. Gravitational wave strain data archived with timing solutions. Neutrino burst catalogues kept with detector thresholds and background noise models. When we say, in the script of this story, that we owe the future a record because their skies will offer fewer clues, that is not sentimentality. It is a technical plan. The more of the distance ladder we nail down in reproducible details now, the less future intelligence will have to rely on fragile chains of oral history about how to reduce a CCD's bias. The calculus of horizons boosts the value of meticulousness. The edge of what can ever be reached, 16 billion light-years in proper distance today, carries one more implication that is often missed. It shapes our sense of simultaneity not only in principle, but in practice. When we say that a galaxy is now a certain distance away, we pick the cosmic time slice where the cosmic microwave background is isotropic. But nothing prevents another observer, in another bound structure, from making their own claim about now. Our two nows can be matched along that cosmic time foliation, but our future light cones' overlaps may not be symmetric. In other words, events that are simultaneous in our best cosmological sense can be mutually inaccessible to influence. This is not news to general relativity, it is its heartbeat. For cosmology, it just becomes visceral. The geometry picks favorites when it comes to conversations. There is no malice in that, only the scalpel of culling. If we want to talk to anyone out there, the hard truth is that out there is a nested set of shells, those who will always be able to hear if they exist, those who will hear only if we speak soon enough, and those we will never reach no matter how clever we are. Cleverness pokes at the edges of physics. Speculations about warp drives or wormholes crop up whenever horizons show their teeth. They are fun, sometimes instructive, and we should not disdain curiosity. But they live in a regime of exotic energy conditions that none of our observations hint at. Workshops on distances in cosmology are not where you sketch a wormhole metric. They are where you refine the BAO scale and track down 0.5% systematics in photometry that propagate into bias on WW. The starkness of horizons is not softened by loopholes. That is what makes the successes of distance measurement feel meaningful. We have learned to make precise statements in a universe that imposes hard limits. If this seems relentlessly global, come back down to the scale of a single cluster and feel how measurements translate into intuition. In a cluster like Coma, peculiar velocities inside the potential well make galaxies deviate from the Hubble flow by 1,000 kilometers per second or more. That smears their redshift positions into needles, fingers of God, that point at us in redshift space. But average across the cluster and the redshift gives a coherent recessional velocity we translate into distance. Cross-check that distance with independent indicators, like the fundamental plane of elliptical galaxies, which relates their physical sizes, surface brightnesses, and velocity dispersions. Or use surface brightness fluctuations in nearby galaxies to get geometric distances. Minute pixel-to-pixel fluctuations in brightness in a smooth galaxy image fall off with distance, serving as a kind of granular ruler. Every rung you add to this local construction reduces our reliance on any one assumption. The long baseline from parallax to Cepheids to supernovae to BAO to the CMB is not a chain with one weak link. It is a redundant, triangulated framework. Redundancy matters most when we push on frontiers that carry philosophical weight. One of those is curvature. Distance measurements pin down whether the universe is, on the largest scales we can see, flat, open, or closed. Current data say, very nearly flat, within tiny fractions of a percent. Flatness does not mean infinite. It means Euclidean geometry holds in our observable patch. Combined with the day-sitter future, we infer that flatness grows functionally moot for local living. The future looks like a set of islands in a smooth ocean, whose curvature you cannot measure with any rope you could ever lay out. But for us now, the fact that the triangles we draw with rulers, built from 150 megaparsec ripples and 380,000-year-old sound waves, add up to 180 degrees, is not a parlor trick. It is a guardrail. It tells us the early universe's physics was such that any curvature was stretched away, consistent with inflation or some cousin. If we are lucky, we will measure the gravitational wave backgrounds from cosmic strings or inflation, adding a non-photon page to our distance book. This is not cosmic favoritism so much as chronology. We are early. Being early is a state of knowledge, not a moral. We do not deserve this vantage, but we have it. So we ask, what will future observers do when their sky's long baselines vanish? They will look inward into isotopic abundances that record the primordial helium fraction. That fraction, close to 25% by mass, is a signature of a hot beginning, not easily faked by any local stellar process. They will scrutinize low metallicity stars in their single giant elliptical for chemical evolution paths that only make sense if the original gas had that helium baseline and deuterium scarcity. They may, if they are fantastically patient and technically audacious, measure the spin temperatures of hydrogen in their halo to infer the absence of a radio background we call the CMB. They may detect, if their instruments can reach, the all-sky stochastic gravitational wave background that inflation or other early universe mechanisms left, but their picture will be pieced together with far less redundancy. The tight geometry that our distance redshift measurements make routine for us will be inference for them. These are not reasons to pity them. They are reasons to write our data so they can read it. Emotionally, the subject is a tightrope. It is easy to pitch into melancholy when you discover that most of the galaxies you see are unreachably aloof and will fade from relevance even as they continue to exist. We do not need to deny that pang. We can, however, metabolize it into a form of attention that is sharper, not duller. In practical terms, we complete as many deep surveys as we can, including in parts of the spectrum that ground-based telescopes cannot reach. We pursue clever, cross-checking methods so that no single systematic can sneak through the net. We share and preserve raw data because future re-reductions with better algorithms will wring more truth from the same photons. We teach the precise meanings of distance early so that sloppy metaphors do not calcify into wrong intuitions. We anchor our sense of far in transformation, not just meter sticks, what distances do to signals, not only how big they are. When we do that, the last piece of this story becomes calm rather than dire. The universe will not stop telling stories because it accelerates. It will tell different kinds of stories, written in different scripts. Locally, there will be exoplanets and biospheres and stellar remnants to study, with distances measured by parallax better than we can dream now. Globally, there will be histories to read out of relics, and for anyone with a taste for causality itself, there will be comfort in the very existence of horizons because they make the immense tractable. They tell us what not to worry about. They draw the map of what we can mean. For cosmo depth, there is a quiet appropriateness to ending here. Our work is to render the abstract vivid, to take the slippery word distance and make it do right by the ways light behaves in a real, curved cosmos. We have stood in filaments and voids, watched clusters magnify background galaxies into arcs, and listened for the faint creak of lines drifting in redshift as the universe changes its pace. We have traced the boundary between what we can still touch and what we can only watch, and we have looked ahead to the time when even watching grows sparse. The distances did turn out worse than a single meaning would allow, but that multiplicity is not a flaw. It is the reason our science works. It is how we translate a sky into a history. So, the coda is an instruction as much as a sentiment. Measure hard while the measuring is good. Archive so that those who come after us can audit and learn. Accept that the map's edge is not a failure, but an honest shape of what can be done. And go outside when the sky is clear. Point your eyes or a telescope at a patch of night and think about which of the points in that field live within our event horizon. Not in some sterile sense of numbers, but in the immediate sense of, could I hear if I spoke? The answer will vary from object to object. The fact that there is any answer at all, some will, some won't, is the most human thing about cosmology. It means we stand in a place where conversations are possible, if only for a while. That is enough to turn the distances from a threat into an invitation. We will not complete the survey of the universe, but while our instruments still drink light from beyond our island, we can do something braver than despair. We can listen. We can measure. We can preserve. We can tell this story true. And in telling it, we keep the universe close a little longer.